Alright, so we're going to be covering the derivatives of exponential and logarithmic functions. And then afterwards, we're going to get into some final tricks of how to find the derivative, most known as using logarithmic differentiation. So the derivative of the exponential, what is the exponential function? So exponential function, its basic form is just y is equal to e to the x, and dy or d over dy of e to the or d over dx of e to the x is simply e to the x, and the proof of that is a bit out of scope because, well, if we were to use the definition of the derivative, we would do like limit as h tends to 0, e to the x plus h minus e to the x over h. And we know that this is the same thing as e to the x times e to the h minus e to the x over h. And then this is e to the x times e to the h minus 1 divided by h. And so we essentially get limit as h tends to 0 of e to the x times limit as h tends to 0 of e to the h minus 1 over h. And we know that this will just be e to the x, and this actually turns out to be 1. And the proof of that, without using L'Hopital right now, is not in scope. So essentially, because this second term becomes 1, we end up getting e to the x. So that is why the derivative of the exponential function is e to the x, which is very similar because you just get the function itself back. So very easy. Now, that's when the base is e. Now, what if you have like a random base x or a, for example, right? So what is the derivative of a to the x? And so one cool thing is we can always represent any random base in terms of e, and then we can always look back at our differentiation rule for e. And so more concretely, this is just the same thing as d over dx of e to the ln a x. So see what I did here, right? I'm basically representing a to the x is equal to e to the ln ax, and this important transformation just allows me to write everything in terms of e to the x, the form of e to the x, which we're very familiar with. And the reason why this works is because, I mean, the log base of ln is just e, so like you can kind of think about this just like translating over to a to the x. So this is, I think, known as like lifting the log or whatever, but this is an important trick that comes up pretty often. But now that we kind of wrote this in this new form that we kind of know how to deal with, we can continue. So that's just d over dx of e to the x ln a. That just comes from the properties of logarithms. Now that's just the same thing as, now we can differentiate this. So d over dx of e to the x ln a is just e to the x ln a. And then we use the chain rule on this, and we can just multiply by ln a, right? And so essentially what we got is the same term back. We know that that's just the same as a to the x, so we have a to the x times ln a. So in summary, a to the x times ln a is equal to d over dx of a to the x. So that's the derivative with respect to any exponential function of any arbitrary base. Now that we have kind of covered exponential functions, let's talk about their inverses, the log function. So let's say we have y is equal to ln x. So again, we'll start off with the easy one where the base is just e. how do we find the derivative of that? And so similarly to how you'd find the derivative of inverse trig functions, we kind of use that property. So let's multiply, or we'll take everything to base to power of e. So e to the y is equal to e to the ln x. And so this is just equal to e to the y is equal to x. And then through implicit differentiation, we know that this, so like d over dx of that is just e to the y times dy over dx is equal to 1. And so dy over dx is simply 1 over e to the y. We know y is equal to ln x, so this is just 1 over e to the ln x. And then we know from before, this is just the same thing as 1 over x. So the derivative of the natural log function is 1 over x. Now, what about the arbitrary base? So let's say we have a function y is equal to log of some base a x, right? How do we find the derivative of that? And so this is a bit more simple than the exponential case, because we know through the change of base formula, this can just be written as natural log of x divided by natural log of a, and this comes through change of base. And so because of the change of base formula, we've just now rewritten this in terms of natural logs, and we're used to finding the derivative of natural logs. And so this bottom term over here is just a constant, right? So we can kind of just treat this as 1 over ln a times ln x, and the derivative of this is simply 1 over ln a as a constant times 1 over x, because we derived it over here. And so we get 1 over ln a times x. And that's the derivative of a logarithm of an arbitrary base a. So now we've derived the derivatives of both an exponential function and logarithmic function. So let's just do some practice problems, and then we'll finally cover logarithmic differentiation, which is a very powerful tool to find derivatives. So let's say we have this function y is equal to log a times a to the sine x. So this is clearly an application of the chain rule. Well, I mean, there's this is clearly an application of the chain rule. Or I mean, the easy way to go about this is first thing you can do is you can, like I said, like think about it. Oh, like clear application of the chain rule, where we treat this as a inner function and this whole thing as an outer function, and use the rules of logs. But sometimes it's very nice to just go back to the basics, and kind of, now that you've seen like a lot of different ways to find the derivatives, just kind of use the tool that's the easiest, right? And we know that through the properties of logs, this is just the same thing as sine x times log a of a. This is just 1, and so we just get y is equal to sine x. And then we know that d over dx is simply cosine of x. And that's solved. So even though we could have used the properties of log and the chain rule to find out the derivative, there's much simpler ways sometimes. But I mean, that's not always going to save us. So let's look at another example. So example 2. So if y is equal to x to the square root of 2, find the derivative. So dy over dx is simply equal to, we can, this is x to the square root of 2. So this is not an exponential, right? This is more like a power function. So this is just square root of 2 times x to the root 2 minus 1. And now let's do example 3. Let's say we have a function f of x is equal to ln x minus 3. Find the derivative. and its domain and range. So pretty easily we know that f prime of x is just equal to 1 over x minus 3. Now, we might be like tempted to say that the domain is just x is not equal to 3, but we have to know where this function came from, right? This function came from ln x minus 3. And we know the log function is only defined for positive terms, so over here it's only defined when x minus 3 is greater than 0, hence it's defined when x is greater than 3. And so by itself, if we were to ignore the fact that this is the derivative of the original function, this is just defined when x is not equal to 3. But we also have this additional constraint of x having to be greater than 3. And so we have to find the intersection of those two domains. And so we get domain is just x is greater than 3. And so that's the domain. And then the range just comes pretty simply. We just find out what happens in this x is greater than 3 domain. And then finally, the most important thing I would say out of all of this is the concept of log differentiation. So logarithmic differentiation is a trick to find the derivative of certain functions when there's really hard to do it otherwise. So let's say you have y is equal to x to the power of x. Now, this is not a power function like we saw in one of the examples, and not an exponential function. Because an exponential function has a constant to the power of x, right? So we have x to the power of x. So both of these terms are varying, right? So how are we gonna find dy over dx? And so the only way we can kind of go about this is to have this like separated out. And how do we separate it out? We use logarithms, right? So if we were to use the log properties, if we were to multiply by log, or take everything under like log, we know that log y is equal to ln x to the power of x, right? Because this is just applying a transformation. And this is just applying a transformation, right? And so what you get is y is now, or log y is now equal to x ln x. And now we can deal with this, right? We can apply the chain rule to find out the derivative. We can apply the product rule to find this derivative. Now we don't have this x to the power of x where we had kind of no idea how to deal with it. So now that we've written it in a form that's more applicable, let's work with it, right? So we're going to use the implicit differentiation formula and product rule here. So a lot to digest. So this is the same thing as d over dx of ln y equal to d over dx of x ln x. Now this is 1 over y times dy over dx is equal to, now we use the product rule, we get ln x plus x over x. And then dy over dx is simply y times ln x plus 1. And then we know that y is equal to x to the power of x. So now our final answer, let me write it over here. Our final answer is dy over dx is equal to x to the power of x times ln x plus 1. And so we were able to differentiate this original function, and notice how there's no other way we could have found out how to differentiate this without using this log differentiation property. So whenever we have something that we can't really apply rules with because we have like some base and then another power where both like have the varying x term, then we can apply the log to split up the power and bring it down, and then use just our normal differentiation properties from there to find the final answer. So that's it. That was log differentiation, that was the derivatives of exponential and logarithmic functions.